Blood flow refers to the volume of blood traveling through a blood vessel, an organ, or the entire body over a period of time. And it can be measured as liters per minute. As that blood flows, it encounters various factors that resist flow and movement of blood, known as vascular resistance. The first factor that contributes to vascular resistance is blood viscosity. You can think of viscosity as the fluid's thickness, or how sticky it is. This relationship is directly proportional, which can be represented as resistance is proportional to viscosity, shown as the Greek letter eta. So this means that as viscosity goes up, it's harder for the liquid's molecules to slide past each other, and so the resistance goes up. Just imagine a heaping stack of pancakes. Then grab some maple syrup. Even when you flip the syrup upside down, it doesn't really come out, and resists moving right away. Slowly it gloops out and doesn't really splash, but just coats those pancakes in a delicious film of sugary goodness. Oh yeah, okay. Now say you have another stack, and you grab some orange juice instead, and then you pour. That orange juice immediately comes out and pretty much goes everywhere. This is because the juice is less viscous than the syrup, and so there's going to be less resistance to movement. Taking a look at blood, there's lots of large proteins in cells, so that makes it pretty viscous, and so it moves a lot slower than just plain water or orange juice. Blood viscosity doesn't change much over time, but certain conditions like polycythemia, which is where a person has too many red blood cells, can increase viscosity. And conditions like anemia, where a person doesn't have enough red blood cells, can decrease viscosity. A second factor that affects resistance is total blood vessel length. Just like viscosity, the relationship is directly proportional, and this can be represented as resistance is proportional to L for length. So simply put, shorter vessels have less resistance, and longer vessels have more resistance because there's more friction resisting flow. This means that as a child grows into an adult, their blood vessels will get longer, and their peripheral resistance will go up. A third factor that affects resistance is blood vessel radius, which in this case is inversely proportional to the resistance, to the fourth power. This means that as a vessel's radius goes down, its resistance really goes up. Unlike viscosity and length, the radius can change from minute to minute, especially the radius of arterioles, which can vasoconstrict, like when you're lying at home on the couch, which would decrease the radius and increase resistance, or vasodilate, like when you're running around outside playing frisbee, which would increase the radius and decrease resistance. Now, the equation relating all these variables is resistance R is equal to 8 times the viscosity eta times length L divided by pi times radius R to the fourth power. Now, keep in mind that resistance is also related to blood pressure and blood flow by the relationship blood flow Q is equal to change in pressure delta P over resistance R. So let's apply this to a real-life situation. And let's say that a person has a blood flow of 300 milliliters per minute going through their carotid artery. And then they suddenly develop a blockage of exactly half the artery, which can happen with a stroke. What would happen to blood flow? Well, a 50% blockage means that the radius is now 1/2 of what it was. And looking at our equation, since nothing else has changed, plugging in 1/2 R for the original R, we get 1/2 R to the fourth power, or 1/16 R to the fourth, meaning resistance goes up by 16 times. Assuming that blood pressure doesn't change right away, subbing in this new 16 times greater resistance, we see that the blood flow drops by 16 times, from 300 milliliters per minute to 300 over 16, which is equal to 19 milliliters per minute, which is a huge drop for just having the radius. So that's how resistance works for a single vessel. But what if you have a bunch of different sized vessels in a row, each with their own resistance, and you wanted to figure out the total resistance? Well, since they're all in a row, one after another, we say that they're in series, and you simply add the individual resistances all together to get a total resistance. This total is called the serial resistance. As an example, let's think about blood heading out to a cell in your toe and back. After leaving your heart, it has to go through an artery, then an arteriole, and then through a capillary alongside the toe cell, and then back through a venule, and finally through a vein to reach the heart again. If we add up all those individual resistances, our total will equal the total resistance faced by the blood flow going to the toe cell and then back to the heart, assuming there are no branches in the system and no other cells to worry about, which isn't really that realistic, but that's okay for now. Another thing to know about this is that when we arrange resistance in series like this, the blood flow through each part of the system is actually the same, even though the resistance at each level will differ mostly based on the length and radius of each vessel. Like I said, this wasn't really the most realistic, because it doesn't account for the millions of branch points in the circulatory system. And for that, we have to think about the concept of parallel resistance. In short, this is when two vessels branch and move blood in parallel, and then meet up again. Which is exactly what happens in the circulatory system, since they start at the same point, and then there's a lot of branching, and then ultimately all the blood meets up again in the right atrium. To calculate the total resistance for these portions where the blood vessels split, we use 1 over R total is equal to 1 over R1 plus 1 over R2, and so on. So let's do another example and use both of these equations. Let's say that we wanted to figure out the total resistance here. In this case, we have 5 different individual resistances to worry about. Let's say that we've got a larger but longer blood vessel with a resistance of 6. And then it branches into 3 other vessels. The really thin vessel in the middle has a resistance of 10, and the slightly larger ones on either side both have a resistance of 5. Then all the branches come back together and connect to a short, wide vessel with a resistance of 2. Now, these resistances do have units, but for simplicity's sake, I'm not showing them. But in case you're curious, resistance is measured in millimeters of mercury times minutes over liters. To figure out the total resistance for this whole system, we need to break this down into 2 parts. And we're going to add up the parallel resistance of the 3 vessels in the middle first. So you've got 1 over 5 plus 1 over 10 plus 1 over 5, which is 2 over 10 plus 1 over 10 plus 2 over 10, which is 5 over 10. Which, remember, in the equation is equal to 1 over R total. So if we flip 1 over R total and also 5 over 10, we get R total equals 10 over 5, which equals 2. So this is the resistance of this chunk of parallel vessels. And this makes sense, because with parallel resistance, the total is always less than the resistance of any one component. Now that we have the combined resistance of the parallel guys, the remaining 3 components are just in series. So we add up 6 plus 2 plus 2, and that's 10, or 10 millimeters of mercury times minutes over liters. And this happens to be around the actual resistance you see in the entire systemic circulation. By comparison, the pulmonary circulation has only about 1/10 of that resistance, and it's closer to 1 millimeters of mercury times minutes over liters. It's also worth mentioning that, just like before, the blood flow through these bits in series is the same, along with the total flow through this whole parallel system. The flow through each of these individual parallel vessels, though, is not the same, since the blood has to split its flow through each of the vessels. Although the sum of these 3 flows must equal the total flow. Alright, as a quick recap, vascular resistance is a measure of the resistance that must be overcome to push blood through the vessels, and can be represented by the equation 8 times viscosity eta times length L divided by pi times r to the 4th. So it's directly proportional to the viscosity and the length, and inversely proportional to the radius to the 4th power. Resistance in series is equal to the sum of each resistance, and 1 over the resistance in parallel is equal to the sum of the inverse of each resistance. What's up guys, Tanner here. Hope you like that video on blood flow resistance, which is kind of like a physiology, physics, and fluid dynamics kind of topic, which is awesome because I used to be a biomedical engineer, so I kind of nerd out about this sort of thing, and I really enjoy doing these videos. So hopefully you learned a thing or two and found it helpful. If you want to do like a deeper dive into this topic and some other topics, you should definitely head over to osmosis.org, which is kind of like our platform where we have a ton of quiz questions, flashcards, and other awesome resources to help you learn medicine. So if you're interested in that, definitely go over there and make an account. Otherwise, you can always support us by donating on Patreon and subscribing to our channel and following us on social media. The people involved in this video were Andrea, who wrote the script. Rishi edited the script. I did the animation and the voiceover, and then Yifan did the editing. So thanks, guys. I think that turned out well. See you later.